In this lesson, we're going to be looking at solving rational inequalities. So we're going to be using some of the same concepts from when we solved polynomial inequalities. Also, we're going to be making use of some of the work we've done for solving rational equations and putting those together. I've put together a list of steps to go through. The first step, actually most of these steps are the same steps that we used when we solved rational equations. So in blue, I've made a note here of something that's going to be different, so I'm going to emphasize that when we get to it in our example as well. So the first thing you want to do, and let's just go straight to this one, you're going to rearrange your equation. Move everything to one side of your equation, set the other side to 0. And we do not cross multiply. I mentioned this in a previous video, and I'm going to go into some more detail in this video as to why we don't do that. Once we have everything moved to one side, we need to write everything with a single common denominator. We're going to want our numerator and denominator factored so that we can remove any common factors by dividing from both the numerator and denominator. Those are going to appear as wholes on our graph, and they're actually also going to appear as wholes in our possible solution. And we'll more on that later as well. Once we have removed any common factors, now any factors that are left in the denominator, any of those that actually can be solved, any of those that are roots, those are vertical asymptotes, and we need to make note of those. In the numerator, we're going to use that to find any zeros, and then from the vertical asymptotes and the zeros, we're going to create what's known as an interval table, sometimes called a sign chart, but I normally refer to it as an interval table. Because it's an inequality, we're going to be creating an inequality that's either greater than or less than. And since we've rearranged it to be 0, for things to be greater than 0 means they're positive, for things to be less than 0 means they're negative. So what we need to then identify are the intervals where things are positive, where the left side is positive, where the right side is positive, where the left side is positive or negative. And we're going to compare that to our 0. And then we're going to write our solution. When we write our solution, we have to consider the restrictions imposed by wholes, by vertical asymptotes, and we also have to take into account any real-world considerations depending on the type of problem that it is. So let's go straight to it. And when I say straight to it, I mean let's not go straight to it. Let's talk about why we can't do cross multiplication, first of all. In a rational equation, you're allowed to use cross multiplication, and I alluded to this, and I even did the first couple of steps in a previous example in a previous lesson. So if I want to solve this equality, this is an equation, I can use cross multiplication so long as I stay aware of the restrictions, and I really should say that here, which is, you can see I have a denominator here of x plus 1, and I have a denominator here of x minus 3. So when I do my cross multiplication, I have to remember that x cannot be, from this one, cannot be negative 1, and from this factor, x cannot be 3. But other than that, I can do this cross multiplication and we're fine. Now, why does that work for an equation but not for an inequality? And I've got the answer over here in blue. If I try to multiply both sides by x plus 1, x is a variable. X can take on a range of values. So I don't know if I'm multiplying by a positive or a negative number. But that's very important with an inequality, because if I multiply both sides by a negative number, it actually flips the direction of the inequality. The same thing is true. I don't know if x minus 3 is a positive or a negative number. So again, I don't know if I should be flipping this inequality. So when I finish my cross multiplication, is this the correct inequality? Greater than or equal to? Is this the correct inequality? Less than or equal to? And to make things even more confusing, it turns out it's not even one of those two answers all of the time, because x plus 1 may be negative at a different time than x minus 3 is negative. And so this actually, not only can we not nail this down to one answer, it could have two or more correct answers. So for that reason, we rearrange, because if I take this part and I move it over to the left side, that's a subtraction. Inequalities are unaffected by subtraction. or addition. It's only multiplication and division we have to watch out for. So that's why I do that. So that being the case, we are asked to solve x minus 1 is less than 12 over x. There's an example. If you've got the textbook, you can see a similar example to this. The first way to think about this is I'm basically taking the graph of x minus 1, which is a straight line, and the graph of 12 over x, which is a reciprocal function, and I'm asking when is this graph lower than this graph. So we could graph this and solve it visually, and I'm going to show you that shortly. But we of course want to develop an algebraic technique to do this. So what I'm going to do is move everything to the left hand side. I could move everything to the right hand side, but traditionally we work off the left hand side, and in this case it's certainly convenient to do so. So I take 12 over x and I subtract it from both sides, so I get x minus 1 minus 12 over x. My common denominator here is going to be x. So I'm going to put everything over x, and that's going to be less than 0. So what did I have to multiply top and bottom by to get this over x? I had to multiply by an x up here. So this becomes x squared. To get this over x, I had to multiply also by an x, so this becomes minus x. And this one was already over x, so that just becomes minus 12. It stays the same. Now I'm going to factor that numerator. It's a simple quadratic. So two numbers that multiply to negative 12 and add to negative 1. That gives me the values negative 4 and positive 3 over x less than 0. And as you can see from this, I have no factors, no common factors between the numerator and denominator, so I'm not going to have any wholes here. I do have a denominator, so the factor in the denominator is x. So now I can say I have a vertical asymptote at x equals 0. And then to find my zeros, I'm going to solve my numerator only. So where does this whole thing turn to 0? My zeros would occur when x equals 4 and when x equals negative 3. These three things, my vertical asymptotes, my single vertical asymptote, and my two zeros, those are going to go on my interval table. And the way that I do this, so let's talk about setting up an interval table. So what we're really doing, before I set up an interval table, let me just describe this using a number line. So what we're really interested in, so we're interested in x equals 0, we are interested in x equals negative 3, and we're interested in x equals 4. And what we're trying to figure out is, based on these three different dividing points, so we've got a vertical asymptote at x equals 0, and we've got zeros here and zeros here. So what we're trying to do is figure out, am I on this side or this side, positive or negative, positive or negative, positive or negative, positive or negative. So we could actually, if we wanted to, we could just start plugging in values here. So for example, I could, in order to test this value, I could just try something like sub, well, a value that's to the left of negative 3 would be negative 4. And we can do this. If we look here, we have a negative 4. So negative 4 minus 4 is negative 8. Negative 4 plus 3 is negative 1. So negative 8 times negative 1 is positive 8 divided by negative 4. So that's positive 8 divided by negative 4. That's equal to negative 2. So my answer here is negative. Is a negative answer going to be less than 0? Yes, a negative answer is less than 0. So this would be part of my solution. From negative 3 to the left would be part of my solution. And would it include negative 3? It would not, because of the less than sign. But that involves doing a lot of mental arithmetic. We're not really concerned with numbers. We're just concerned with the sign, positive or negative. So this is a really awkward way to do these things. So instead, that's why we use a slightly more condensed streamlined way of doing this, which is something known as an interval table. It actually looks very similar. So we're going to use this same idea. So what I'm going to do is actually I'm going to put a vertical line for each of the values. So there's -3, there's 0, there's 4. And then what I'm going to do along the side here, I'm going to break it up into a chart. And here I'm going to put each of the factors. So everything's in factored form already. So I actually need another line here. So here are my factors: x minus 4, x plus 3, and x. And that's fine like that. And so now what I can do is, rather than trying to do all of this at once, I'm going to go a little bit lower here. So let's fill this in, and then I'll fill in this last row at the bottom. So let's choose a number. I'm going to choose a different color. So let's once again put a -4 in there. So if I put -4 in here, -4 minus 4 is a negative. -4 plus 3 is also negative. And -4 replaced for x is a negative. So these are either multiplied or divided in some way. So the way we combine those is we just go negative times negative is a positive times a negative gives me a negative as my result. So that's what we're looking for here. This is the overall result. Is it positive or negative? And I do the same thing here. So let's choose a number. How about -1? -1 minus 4 is negative. -1 plus 3 is positive, and that's negative. So I have two negatives and one positive. That's a result. That's a positive, because negative times negative is positive, times positive is also positive. Let's try 1 here. 1 minus 4 is negative, 1 plus 3 is positive, and 1 is a positive number. So those become negative. And let's try 5. 5 minus 4 is positive, 5 plus 3 is positive, and 5 is a positive number. So this is overall positive. Now, we've got enough room. I can fit it all on there. Notice I just focused on the factors here, but my inequality, I'm looking for something that's less than 0. Well, what kind of number is less than 0? That gives me this one is less than 0, but this one is not. This one is less than 0, but this one is not. So my intervals, my solution, is going to be less than 0. That lines up with this -3, but as I was mentioning before, it can't include -3. So we end up with that part of this one. And then this fails. And then I come over here. Well, this is less than 0. But again, it's just less than. So it cannot include here. Well, yeah, it can't include the 0 because that's actually an asymptote. So it can never include that. But it also does not include the 4 because it says less than 0. It doesn't say less than or equal to 0. So now I have I've used the number line to show my solution, and what I really should do is express my solution also in an algebraic notation. So how do I express this algebraically? I could say x less than -3 or 0 less than x less than 4. That's one way I could express my solution. I could also express my solution using our interval notation. I could say x is a member of, this one is -infinity to -3 with a round bracket because it doesn't touch -3, comma, 0 to 4, not including either of those. So there's my solution using an interval table. If we look at the graphs, we wanted to know when this line, x minus 1, was less than the graph 12 over x, which is this red line. So where is the blue line below the red line? And you can see here are those dividing points at -3, at 0 because of the vertical asymptote, and at +4. So looking here from -3, that's where they meet. So where is the blue line less than? Yes, it is. So that one is correct, from -3 to -infinity. But now the blue line is above, so this one fails. As soon as we hop over the asymptote, the blue line is now back underneath the red line. So this is a pass again, and this is a fail. And that's the exact same solution we came up with algebraically. The other thing to consider is that we moved everything over to the left side, so we actually solved this inequality graphically. I used technology to graph this, and what do you notice? Here is that dividing -3, so that's a key point. 0 is key because of the asymptote, and 4 is key. So all of those key values are still here. This is below the x-axis. This is below 0, so that gets a check. That one gets an X because it's above the x-axis. This is below the x-axis, gets a check. This one's above the x-axis and does not, gets an X. So it means the exact same thing. Okay, let's try one that's a little bit more involved. So I've been asked to solve this. So what I'm going to do is bring everything over to the left side to start. X over x minus 1 minus 5x minus 3 over x minus 1 times x plus 1. Now you can see the factor that's missing. Oh, sorry, and I have to say that's now less than 0. The factor that is missing from here is an x plus 1. So I'm going to write that as x over x minus 1, and recognize that to make that a common factor, I need an x plus 1 here and an x plus 1 here, minus 5x minus 3 over x minus 1 times x plus 1 less than 0. Now I could have combined these all at once, but I just wanted you to see that. So that becomes x times x plus 1 minus, now this is minus this whole numerator in brackets, so this is minus 5x minus 3 over x minus 1 x plus 1 less than 0. Remember, we want factored form. A lot of students see this and their first instinct is to say, hey, that's a difference of squares, I know what to do there. We want this factored in its form that it's in right now, so we leave that alone. X times x plus 1, or sorry, yeah, x times this whole factor, so x times x is x squared, x times 1 is plus x, and this becomes minus 5x, and negative of a negative becomes plus 3, over x minus 1 times x plus 1, and that's all less than 0. So I end up in the numerator with an x squared minus 4x plus 3 over x minus 1 times x plus 1, and that's all less than 0. Last step of this algebra side is going to be to factor this. Two numbers that multiply to positive 3 and add to negative 4. That's x minus 1 and x minus 3 over x minus 1 x plus 1 is less than 0. And now I can divide out this x minus 1 goes into x minus 1 one time, but that means now I know I have a whole at x equal 1. Or that means I have a restriction, which is that x cannot be equal to 1. And that restriction is what we're going to be making use of. So in the end, I end up with this x minus 3 over x plus 1 less than 0. And from here, my vertical asymptote is at x equals negative 1. And my zeros, I only have one of them, and that occurs at x equals 3. So my interval table only has to have these two numbers on it. And so when you're setting up your interval table, you need one column for your factors, And then you need vertical lines for these two features. So there are two of them here, so I need 3 more columns. That means I need 4 columns in total. So 1, 2, 3, 4. 1, 2, 3, 4. And then what I do is along the top, I'm going to put, let me just reduce the size of this a little bit. Okay, so along the top, I'm going to put my, did I put too many? No, it's right here. So -1 is the vertical asymptote. 3 is one of my zeros. And now I'm going to put in my factors. So I have 2 factors. So one of those is x minus 3. One of those is x plus 1. And then I need some room for my result. So I didn't actually need, and you don't have to be exceedingly, you want it to be neat enough to be able to follow. I need to be able to see and understand what you're working with. And then you choose some values here. So what values, and I'll switch to another color. So less than -1, -2 seems easy. Between -1 and 3, now I have to be careful here. Technically it shouldn't matter. I could actually use this value, but since x is not allowed to be 1, I'm going to use 2 here, because I don't want to get into the details of why we should or shouldn't use this. This is a restriction, so we are going to be making use of this in a moment. And then bigger than 3, I'm going to put a 4. So when I put -2 here, -2 goes in here. That's -2 minus 3 is -5, so that's negative. And if you want to, there's nothing saying you can't go ahead and put the numbers in. Let's put the numbers in this time. -2 plus 1 is -1. The result, now this is where you don't want to do a calculation, and this is why I don't bother with numbers, because it doesn't matter whether this is multiplying or dividing. I've got 2 negatives here. My result is positive. So now when I put a 2 in here, 2 minus 3 is negative. 2 plus 1 is positive. The result is negative. And then finally, I put in 4 here. 4 minus 3 is positive. 4 plus 1 is also positive. My result is positive. Now, looking at those results, which ones pass, which ones fail? Here is less than 0. I want this thing to be less than 0. That means I want this thing. So I want a negative result. So which one of these gives me a negative result? Well, it looks like this one gives me a negative result. These two are giving me positive results. So this is my solution. So my solution would normally be from -1 to 3. Let me just show you that on the number line. -1 to 3. Does it include -1 or 3? It does not. So it's an open circle here and an open circle here. And normally I would just say, okay, connect those together. But I can't do that. And the reason why I can't do that is because I have a hole at x equals 1. And so I also have to mark 1 on here and put a hole there. So my solution ends up being from here to here, and then from here over to here. And so I express my solution as x is a member of the interval from -1 to 1. Union, I'm going to be a little more sophisticated here. We've been using commas. There's also this thing in set theory called union, which is saying it's the combination of these two. And I'll accept that if you use that. So it's the combination of these two. My solution could be between here and here, could be between here and here. This is also like saying x is a member of -1 to 1 or 1 to 3. Same thing. So that's one way to write it. That's another way to write it. And a third way we could write this is we could say, let's see, we could say -1 less than x less than 1, or 1 less than x less than 3. All of those are valid ways of representing these solutions, and really we should also, now this is implicit here, but it wouldn't be the worst thing in the world to mention that x is a member of the reals here. Just go back up. I want to make sure I've actually answered the question. I have. And if we move forward, I didn't include a graph of that one. Okay, so straight on to your homework, keeping in mind those steps and the importance of the wholes versus the vertical asymptotes versus the zeros.